All right, everyone, we're back. We're live again. Let's take 2 minutes, form into your self-selected groups, and I want to hear the famous buzzing of the 2450 class to answer these 4 questions. All right, you got 2 minutes.
So regression's like, here's some points, yada, 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 and then here's like a line that fits through the points practically by taking the least square root, yada, yada, yada. Yeah, that's it. And then least, what is the quantity that's between lines? Like the distance between that line and yeah, the points. It's like a triangle. It's like a triangle, yeah. Like Pythagorean.
Nick, working by yourself? Working by yourself? He's with the academic masochism. All right, join in, join in. What was your team's name? Team Jacob. Oh, I haven't seen that. Okay, Team Jacob. Okay. I'm old. All right. I cannot clap as loud because IKEA caused me a paper scratch over here. What? All right, we start with academic masochism. In a few words, describe the idea of regression.
So basically, you're just trying to find like a pattern within like a set of points,
right? Yeah. Sometimes when you have data scattered all over, we saw how interpolation is just horrible because the data is not following one unique trend. Rather, it's following an average trend, a direction trend, given all the uncertainty in the data. And the idea of regression, hey, let's fit a best curve in these data points. In least squares regression, so that's the idea of regression. Now, we can do regression based on different things because obviously, the system is not closed. Okay, so we have more equations than there are unknowns. So we need one more condition. Think of it this way: we need one more condition to close that system to find a solution. One of these ways is what we call least squares regression. So what's the quantity being minimized? We go with triad. The triads. Which error? It is an error. It is one type of error, right? But which error? Yes, it's between the predicted value and the input value, but what do we do with that? Pardon me? No, I pointed at you.
For the answer?
Yes.
The error of the square.
Yes, so the error, we take the error that the triads have described. That's the difference between the predicted value of your model and the data, the input data, and then you just take the square of that. You add them all up. That gives you the squares, and then the least squares we're minimizing. We're taking the least square error. Okay, that's what the data fit does. What is the simplest? Now, once we derived, regression, linear regression for a straight line. And then we started wanting to look at, and then we measured, I think, Amber's height, right, using the femur, and then we noticed there was an error in the prediction, and then we wanted to look at how well our data fits, and then we started looking at descriptions of data points, of data, how we describe data. So what's the simplest description of a set of data? Back corner. Yes, the mean value. In the absence of any knowledge, okay, if you take statistics, if you become well-versed in statistics, in the absence of any knowledge, you're given data, the best description of that data that minimizes the uncertainty is the mean value, is the average value. That being said, what is the standard deviation? Trevor, your team, this standard deviation. Pardon me? Trevor, behind you.
I'm still looking at it.
Okay. Any takers? Natalie.
The magnitude of error prior to regression with respect to the mean?
No. Well, yes, but that's, yeah.
That's like the average distance from the regression line?
No. That's the standard error. Emily.
So
I know you know the answers.
it talks about kind of like the sparsity of your sets.
The spread. Okay, so now, yes. Now that we said that the mean describes the data, obviously some of the data falls above the mean and some of it falls below the mean. How can we assess that? Can we assess that spread around the mean? Yes, and we do that with the standard deviation. We took, again, the distance between the data points and the mean value. We squared them, took the sum of those, and computed an average distance, okay? If you remember, I'll go through just very briefly. Yes, so if the blue line was the mean, and those pink lines were the distances from the data to your mean, to the average, the sum of the squares of those divided by the number of points, and then you take the square root of that, that gives you an average sense of how far away the data is on average, okay? And we call that the standard deviation, okay? And then you typically describe the data as, plus or minus 1 standard deviation. You probably hear things in the news saying, or looking at data plus or minus 1 standard deviation for normally distributed variables, and you'll learn what that means in statistics. But essentially, for most things that we observe in nature, 68% of the data falls within plus or minus 1 standard deviation. And 95% of the data falls, 96% falls between plus and minus 2 standard deviations, okay? Now, this was done for the mean value, okay? Now, we're going to define standard error, okay? What is standard error? The same way we looked at data and the mean value, now, with regression, we did better than the mean value. Probably. Don't you agree? So if you take the mean value, it was going to give you a horizontal line, right? With regression, we got a line that kind of follows the data in general. So we expect to do a little bit better than just using the mean value to describe data. Agreed? Okay. Right? So again, remember my nomenclature, Y model, given by F. It's A0 plus A1x, and data points Fi. The predicted value with our model, they're called Fi. It's the application of the model at the points Xi. Okay? So again, the same analogy here to the standard deviation applies to the regression line. The regression line divides the data into 2 regions, data above the regression line and data below it. Okay? And again, each point falls within a distance, yi minus fi, from the regression line, okay? Again, remember what we did with the mean value. We looked at the distance from the data points to the average. Now we're looking at the distance from the data points to the best fit, to the curve that we are trying to model the data with, okay? Now, you see where I'm going, okay? Where I'm going is I want to define a sense of the spread of the data around the regression line. The standard deviation helped us define the spread of the data around the mean value. Now we want to define the spread of the data around the regression line. Why is that important? Well, because it tells us how well our regression line is doing. Okay? Did we expect a good regression will mean that you have reduced the spread of the data. Okay? We have reduced the spread. So let's see how this works. Again, the aggregate distance of all of these points is the sum of yi minus fi for all of these data points. When we were looking at the mean value, we had y bar over here. Right now, we have a better guess than y bar. We have fi, which is essentially a value for each data point. We have a different value for each data point. Okay? So now we can compute the average distance from the regression line, okay, the same way we did before. If the total distance was sum yi minus fi squared, we can now compute an average distance from the regression line. All right? That's your activity now. You got 2 minutes, just like what you did last time when you computed, you helped me compute the standard deviation. I want you to compute an average distance from the regression line. You have the total distance over here. You got 2 minutes. Give me an average for that distance. And remember the units, okay? I'm not going to ask your group because you're right. Because you're right. He is right. Yeah. Well, your group is right, right? So unless you want to secede from the union. Good call. Okay, so you have an answer. But somewhat. What is I?
Oh, sorry. That means it's the number of points. That would be like n or something.
Okay. But then, so here, this is not y bar. Oh, this is. Oh, so the mean. Yeah. Okay. Okay. Yeah.
So we were talking, and we were wondering why the equation is n minus 2 when you divide it on the bottom for.
So you're looking at the slides, I suppose. Well, so no, that's fine. I'll explain that because you know 2 degrees of freedoms for the data. You know 2 data points already, which are the coefficients of the straight line. So that reduces your data set by 2 points. Similar to what we did with the mean value, because the mean value, you could deduce the last point by knowing the mean value and the n minus 1 points. You could get the last point essentially because their sum, it should be equal to, that average is equal to the mean value, right? So same thing here. Okay. All right. So most of you have an idea of how to calculate this. Felicity, do you want to share your thoughts?
Yeah.
What your group, yeah?
So you said you would do like what the formula is
Uh-huh.
there, and you would divide it by n. We said n minus 1 just because of what we talked about
Uh-huh.
last time with the degrees of freedom. But
Okay.
I'm not sure if it's exactly n minus 1 or 2.
Okay.
Depending on what it is.
What about the units?
And then, like, a
Square root, correct. So the square root will give you the correct units. The question is, what do you divide? What do you divide by? So I have 3 schools of thought based on my wandering around, and I want to get some hands. So who thinks n goes in the denominator? N goes in the denominator. Okay. Okay, just n. Who thinks n minus 1? I know many of you have been looking at the slides, but you better, if I pick you, you better know how to explain. Okay, so I got like 5, and then what about n minus 2? Okay. All right, so the correct answer is n minus 2 because you've seen it on the slides, but who would care to back this up? Not Connor.
The only person who
Nick,
raises his hand.
yes.
It has to do with the degrees of freedom.
Yeah?
I don't know exactly where we remove our degrees. But we have too many degrees of freedom, and so we need to subtract 2 from our set because
It's a regression line. Yes, you are correct. So in other words, when you think about the mean value situation where we said that the mean value actually gave us 1 extra degree of freedom. So if you know the mean value and you know n minus 1 data points, you can deduce the last point just because the mean value is equal to the average of all of those points. Okay, so that being said, if you're given the mean value, you lose 1 degree of freedom. Same thing here with the regression line. You're given 2 degrees of freedom. These are A0 and A1, the coefficients in the regressed line. So that knocks down 2 data points from your data set. And then the correct answer is to have n minus 2 in the denominator. Now, for large data sets, this doesn't make a big difference, okay? As n approaches infinity, this is insignificant. But this is the mathematically rigorous formula for what we call the standard error. So the standard deviation, we call that SY because that was independent of the x location, or that was independent of the independent variable. Okay, it was mean value for the entire data set. However, with the standard error, we say SY given x because of this FI. And FI is the value of the model evaluated at xi. So for each point yi, you have a different value of fi, okay? F of xi. And that defines the standard error. It measures the average spread of the data around the regression line. And also, data would be presented in a similar fashion to how we present the standard deviation. You present data average plus or minus 1 standard deviation. Yes?
Is it an average distance up and down or perpendicular?
It's up and down. It's up and down, not perpendicular to the line. Okay, so it's just vertical. Okay? So then you would have plus or minus standard error around that line. And for normally distributed variables, these are, follow a bell curve. Again, 68% of the data falls within 1 standard error. The standard error is powerful because you could say, my prediction of the femur height is whatever, number we had, 168 plus or minus 6 centimeters, right? So that's what we would say in this particular case. I think the standard error for this particular problem was 4 centimeters. We'll calculate it in a second. Anyway, but more specifically, it represents the average distance that the observed values fall from the regression line. It tells you how wrong the regression model is on average using the units of the response variable being, the y data in this case. Okay. Now, so we have the standard deviation right now. We got the standard error. Okay, but that's not the entire story. We're going to combine these two and create a measure that tells us how well our regression fits our data. Okay, how well our regression does. Because you could say here, you could still say, my standard error is small. But how do you, what do you compare that to? What is small? What is a small standard error? Is 5 centimeters small? Is 2 centimeters small? One thing you could say is I'm going to compare my standard error to the standard deviation. If my standard error is smaller than the standard deviation, that means that regression did better than just using an average value to describe the data. Again, if your standard error, if the spread of your data around the regression line is smaller than the spread of the data around the mean, then you did better than just using the mean to describe the data. So in other words, if you rotate this and make this look like it's a mean value, you've essentially reduced the spread of the data around the line. So that's the question we want to answer. So the next step is to compare the standard error to the standard deviation. Why do we use the standard deviation as our baseline? It's because that's the best thing we can do in the absence of all available data, is use the mean value and the spread of the data around the mean value. Okay. The next measure combining these two quantities is called the coefficient of determination, or R squared value. Okay, let's go through some thinking. For when we use the mean value, that gave us the standard deviation, and that was the formula for it. And it essentially, so what I'm going to call this summation, I'm going to call this summation ST, because that was the distance, okay, the average distance from the mean, okay? Not the average distance, sorry, that's the sum of distances from the mean value, okay? Call this numerator ST, okay? This describes the magnitude of the error prior to regression with respect to the mean. So that's essentially what I just said, is independence of all information, the standard deviation, or this quantity ST, measures how the total error, the total distance of your data from the mean value. Okay? When we did regression, we came up with a different measure, which is equivalent to the standard deviation. It's nothing more than a standard deviation around a regression line. And that measure gave us this formula. I'm going to call the numerator here, we'll call it SR, for summation of regressed values. And it essentially measures the magnitude of all of the errors or the distances from these data points with respect to the regression line, okay? So this characterizes essentially the error that remains after the regression, because we set off with a hypothesis saying the mean value only gives us so much. We can do better by doing regression. Let's do regression. This quantity here, SYX or SR, quantifies how much error we still have in our regressed model. If all the points fall on the regressed line, SR would be 0. Okay, so we would have improved, right? But it's not. So that quantifies whatever is left in terms of explaining the data. Okay, so now I said I want to combine these two quantities, and obviously they're combinable. So let's see how we can combine them. Okay. Now the difference between these two errors means something. Okay, and I want you to think in light of what I was talking about. You know, holding the mean as essentially the holy grail, as the gold standard, and then we did the regression. Now the difference between these two, the error committed in the regression versus the error committed with respect to the mean, it means something, okay? So I want you to think about it, give it your best shot. Remember, ST is the distance from the data points to the mean, the sum of all distances, the total distance, and SR is the distance of all the data points from the regression line. Okay? Think about what the difference means. You got an answer?
Yes.
Okay. Pardon me?
The distance between the regression line and the mean?
No. Think about the sentences. Think about the sentence. I want something more into it, something you can explain to your grandmother, something very basic, very intuitive. You know, think about the sentences I have up there, okay? You have a question?
Is this a fair way to look at it? It's like when you mentioned you take the regression and then like
Okay. Okay. Uh-huh.
your mean,
And you sure? Yeah, uh-huh.
and then like this is distance.
Okay. So, but I want you to translate that into words. Something you can explain intuitively.
So like how like if you have a larger difference, then that means that your linear regression is doing much better.
Larger difference. Yes. Okay. All right. So we got some interesting answers. All right. This is the type of mentality you want to be in when you are trying to explain things. Is explain it in a way. You know, there's a saying in research that says if you want to publish a paper in Nature or like one of these fancy journals, you know, make sure that your grandmother can understand it. Okay, assuming your grandmother doesn't have a PhD in whatever you're doing, right? And so, but that's really true. You know, that's the elevator. We call also that the elevator pitch. You know, I heard some of you talk about slopes and distances. I want something very intuitive. So, do you have any takers?
I'm just gonna make a guess, not that like I know anything, but I see the words prior and after. And so maybe it's like the magnitude of error during regression.
Okay. Brandon had an interesting thought.
Well, it's
Almost. Yeah.
like the distance between like how it's the difference between the average distance between where the points are going to be relative to your line. So
Okay. So I like your last idea that you mentioned to me. What happens if this difference is large or small? Katie.
It just represents the difference in the errors when you use standard deviation in the regression, so it represents how much better the regression is.
Okay, along those lines. I'm going to go back to Brendan. So what happens if the difference is large or small?
if this distance is large, then that means that your regression is significantly better than
Better. Okay, and
I was going to tell you, it tells you how horizontal the regression line is.
no, not quite, Trev. Yeah. Well, remember, we're taking the difference between two errors. One error, Nick.
It's like the amount of error made, like
Yes, yes. So you know, we're all heading to the same direction. Essentially, what we're measuring here is the difference between two errors. One, prior to regression, that's our baseline error. Then we did regression, okay? And then we had another error. If we take the difference between these two errors, it tells us how much improvement we made by using regression. If no improvement was made, then both values would be the same, and then this quantity would be 0. So horrible. No, we didn't do any improvement. But if this quantity is infinite, then we've infinitely improved our regression. Think of it this way, okay? If ST is much larger, if SR is much larger than ST, it means that we have significantly improved our regression, okay? Yes, Nico.
you just say it's how much more accurate.
Yeah, compared to the mean, okay? Compared to using a mean. Okay. So the difference between the two quantifies the improvement that the regression has made over just using a mean value to describe the data. Connor, yeah.
So, I guess I'm kind of confused. If SR is bigger, we've infinitely improved?
Hold on. I'll show you the next formula. If SR, so the difference needs to be large. If the difference is large, but that's still, a relative measure. So we're going to do a better measure. If the difference, thank you for catching that. So it's not SR. So in other words, if SR is 0, if SR is 0 and ST is the one versus the mean, then we've eliminated all errors, right? But that's not quite what we want. So let's take this one step further. Again, we said the difference between ST and SR measures the improvement we've made. We started with an error based on the mean. We did regression. What happened to that error? So the difference measures exactly that quantity. What happened to that error? Okay. If SR is approximately equal to ST, we didn't do any improvement, right? Because the distances from the mean and the distances from the regression line remain the same. We didn't do any improvement over using the mean to describe the data. However, if SR is much less than ST, then we have made significant improvement. In other words, we shrunk the distances from the regression line. Okay, all the distance from the regression line are small. Just one more step before you leave. Okay, now because these quantities are scale dependent, it's best to normalize by one of them. So we normalize by the quantity, by the distance from the mean value. Okay, and we define what we call the R-squared value, or the coefficient of determination. And that, we claim that this tells you how good of a data fit this is. It's ST minus SR. That measures the improvement in error over the original error. Okay, this is always a positive quantity and is often written by this in this way, 1 minus SR over ST. As R squared approaches 0, you have a bad fit. So when does R squared approach 0? It's when ST and SR are equal. So you started with ST based on the mean value. You did regression. You still had the same errors. You didn't improve anything. So SR over ST would be 1, and 1 minus 1 would give you 0. A good fit is when SR is pretty much 0, when we've eliminated all the distances from the regression, and that gives you a perfect fit. Now, this is hint, hint. If you get data with R squared equal 1, that's either a fabricated problem or someone doctored the data. Okay? In homework, I'll give you data with R squared equal 1 because we fabricate the data to illustrate a point. But in real life, you'll find values like 0.8, 0.89, 0.9. Okay? So the larger the R squared value, the better your fit explains the data. Again, compared to the mean value, we did regression, we shrunk the distance. Did the distances shrink? If they did, then the R squared would be closer to 1. Okay, I'll see you on Thursday. Please come 10 minutes earlier, so 1:50, okay? And that will be candy. I will be bringing, I couldn't find potato wedges for you. I'll get you deep fried chips, if that works.